Alright, let's see here. On our reminders, there's a group quiz at the end of class today. You have mastering due tonight, like a third of you have done it already. Good job, superstars. We'll do an individual quiz on Monday. You have your exam coming up. You have your final coming up. School's over in less than a month. Yeah, if we're counting, there's like 10 more lectures. So, if you are not making time to study now, I would. Just saying. Alright, so the last thing we did on Wednesday was, let's see, where's my picture? Alright, we had that pretty graphic. Right, and so we had the anode and the cathode and the bridge in the middle. So it would be really hard and time consuming for me to ask you to draw this every single time I wanted you to draw this equation as a cell. Right, that would be a lot of effort on your part. So electrochemists, like myself, have to come up with a shorthand to help you draw these faster but tell the same information. So, I don't know where you want to put it, if you want to put it on the same picture or just below it. What we're going to do is for the same picture, so the shorthand for the picture above this, copper at the anode, silver at the cathode, salt bridge in between. We're going to put all the items that are in the anode, we're going to draw them first, right, because the anode comes first, anode, bridge, cathode. So everything at the anode, and we always start with the solid phase of whatever metal we're looking at. So copper solid. Okay? And then for shorthand, I'm going to draw an up and down vertical line. What's the other version of copper that's in my anode? Yep, copper plus 2, aqueous. Okay, is there anything else on that side of the beaker? No, right? So we're going to draw a double line meaning salt bridge. And this side is everything anode. Alright, so now I'm on the other side of the salt bridge. What is the ion that's in solution at the cathode? Silver plus 1. Is there anything else in there? No, right. Okay, that's the only ion. What is the metal that's at the cathode? Silver metal. So this shorthand tells you all the same information, right, that the double beaker drawing picture tells you. It's just much easier to draw. This tells me that the anode, so if the anode is at an oxidation or reduction. Oxidation, good, right? So it's telling me that the copper is going through the oxidation reaction and the cathode is going through the reduction reaction. And all together, I have a redox reaction. So let's do some other problems like that. Other salt bridge cells. Alright, so let's say example 1. If you had written smaller, we would have all fit on one side. It's my fault. Alright, so I have 2 chromiums. That's a solid. Big old S. And 3 iron plus 2 is making 2 chromium ions and 3 iron solids. How would I know if this equation is balanced or not? What are the two things you have to look at? Right, we're going to call it mass and charge. Right? So mass-wise are the same number of chromions on both sides of the arrow. It's the same number of irons on both sides of the arrow. Mass balance. Done. So now let's look at charge. Is the charge going in equal to the charge coming out? Yes. Right, I got plus 2, I got 3 plus 2s, and I got, oh, that should be a 3. 2, 3 pluses. This is supposed to be balanced. Yeah, it should be 3 plus 2s and 2 plus 3s. So if both those things are correct, if you both have mass balance and charge balance, then you do not have to break it into half reactions and fiddle with it. It's all set, it's ready to go. So now I would like to draw in shorthand anode, bridge, cathode. So in order to know what's at the anode, what reaction does it have to be undergoing? The oxidation one. What thing is being oxidized? What is increasing its oxidation state? Chromium, right? What's the state over here? It's a solid, so what charge should it have? 0. So I'm going 0 to plus 3. Alright, that's an increase, so that is the oxidation half. Alright, so start off with your solid. What's the thing I left off of this Cr3+? The 2, because it doesn't matter. So I'm not trying to show that it's balanced. I'm just showing you what is physically in the beaker. I'm just saying when I have the beaker, there's chromium solid in there and there's chromium ions in there. You could certainly go back and balance it on your own. You needed to do that for a separate question. Alright, so then what is being reduced? The iron plus 2, right? So it's going plus 2. What's the state of iron as a solid over here? How is iron normally found in nature? It's a solid, right? So it should be 0. Alright, so then on this side, done. Right? Tells you all the same information, just much easier to write. It does. It does. So we always put the solids on the farthest outside, and we always put the ions closest to the salt bridge, just by standard procedure, I guess. I mean, if you're looking at the picture, right, I'm literally reading this picture. I'm going metal, ion, bridge, ion, metal. And so just imagine that that's what you're trying to tell the person. There's a piece of metal, then an ion, across the salt bridge, ion, metal. Alright, let's do one more of those, then we'll get into something more interesting. Hard to believe that you guys aren't super excited about this. It's the best. Let's do... That's a good one to do. Ooh, what if we do it in reverse? What if I give you the cell and you tell me the balanced chemical reaction? How exciting would that be? Pretty exciting. Good. Alright. Tough crowd today. Is it the rainy weather that you got down? Yeah, okay. Wish you were back in your room napping. Alright. Let's say I have this. Alright, so let's say that is the cell. Question is, what's the balanced redox equation that makes this cell up? Alright, so what is a good way to kind of get this started? Any suggestions? We could do it by 2 half reactions. I think that's easiest, and then recombine them. Right? So let's look at the anode half reaction. If it's the anode, I know it has to be written like this. Right? Because my oxidation state has increased. I've gone from 0 to +3. The anode's where the oxidation is, so that's the only way to write that. That the iron gets oxidized. Right? But what if I wrote iron +3 goes to iron 0? What's happening? It's a reduction, so it can't happen at the anode. So the only way for things to happen at the anode is for it to have an oxidation reaction. Alright, so where should I put the electrons? Who needs them, the reactants or the products? Right. That. Okay. Questions on it? Questions? So now this side equals 0 and that side equals 0. Everybody's all zeroed up. Okay, good. How do I know if this is the reaction that occurs at the cathode? What's happening to my copper +2? Being reduced, right? So if it's being reduced, where do I put the electrons? On the reactants, and how many does it need? 2. Can I add these 2 equations together right this second? No. What do I need to do to my iron reaction? Okay. Then what do I need to do to my coppers? Good, we can now go backwards and forwards. Alright, let's see here. It depends on your computer. I think it's shift backslash. Yeah, no, and the backslash is the one underneath the backspace. Let me move my keyboard over. You can see it. Oh, maybe. Oh, there we go. Okay, it's this one. That one's backslash. This one's forward slash. So if you do shift this one, you get question marks. If you do shift that one, this little double dash is an up and down vertical line. So, and it's gonna, if you have an apple, it'll be the open apple key, similar key stroke. So, yeah, it's confusing because the instructions say use the backslash key. You may think it's this one, and you end up with question marks all throughout your question, which you may actually have that many question marks, but that's not what it's asking for. It's asking for this up here. So. Alright, well, let's talk about what's next. Ooh, calculations. Alright, so the driving force behind a spontaneous reaction, if it's spontaneous, what's its delta G value? Greater than 0, less than 0, or it is 0? Okay. So the driving force behind a spontaneous reaction in a voltaic cell is to be measured by what's called cell voltage. Alright, so cell voltage is going to depend on what redox reaction you're using, right? But it also depends on the concentration of all the species in solution. So all the ions and whatnot affects the cell voltage. So if I have something called standard cell voltage, and I put that little superscript circle up there, what does that automatically tell me about the temperature that I measured it at? Right, it's going to be room temperature, 25 to 98 Kelvin. What does it tell me about the pressure of the atmosphere? 1. What does it tell me about the concentration of ions? Can't be at equilibrium because delta G would be 0. But what concentration? What is a good standard number? 1. That's what concentration we're at. 1 molar. Why cannot be 0 molar? It doesn't make any sense. So it's definitely not 0. A lot of the other things are 0. In this case, standard cell voltage is measured at 25 degrees Celsius, right, 298 Kelvin, 1 atmosphere, 1 molar. That makes things much easier to calculate for starters. Alright, so for example, let's say I have this reaction. Let's say I've done this reaction at 298 Kelvin. Am I at standard state for everybody? Why do I not need to tell you anything about the solid? Doesn't matter. It's a solid, right? There's no concentration or pressure that affects a solid in these cases. Right, so this at 1 molar, that's at 1 molar, and that's at 1 atmosphere. So I'm at standard state. So you would, we'll show you how to calculate it here in a second. But let's say you had this all set up and you hooked your little voltmeter up to it. It has standard state voltage of 0.44 volts. Is that a positive or negative voltage? Some softballs here. Yes, positive number. Excellent. Positive voltage. Is that now spontaneous? Based on what we said on Wednesday? Yes. Yes. Good. Okay. Positive voltage, spontaneous. So then what should the delta G for this reaction be? Positive, negative, 0? Negative. It would have a delta G. So, how did I come about this number 0.44 volts? I am glad you asked. It comes from calculating it. Alright, so any redox reaction, like we've done a bunch of times now, can be split into 2 half reactions. Each of the half reactions has its own standard state potential, and therefore its own cliffhanger. What did I want to say there? I have no idea. Overall. 0. Apparently I got distracted while typing the slides. And I was like, okay, who knows what happened. Probably a squirrel ran by or something. Alright, so if each half cell can have its own E0 in its own overall. Right, so the E0 of the reduction half reaction we call E0 reduction, red. Right, so far so good. Right, oxidation gets a subscript ox, the other one gets red. Pretty straightforward. What half of my 2-beaker cell do reductions occur at? Anode or cathode? Where should I look for my reductions? Cathode. Right, so those will be used interchangeably. Sometimes they're E0 reduction, sometimes it's E0 cathode, telling you the same information. So what should be the other name for E0 oxidation? Anode. All right, looking back at our picture briefly. Here we go. Where are the electrons ending up? Right, they're going from the anode to the cathode. If I want to figure out the total number of electrons that have traveled, I'm going to do cathode minus anode. Right, so this is where they all ended up. And I want to know how many were left. So the total difference is going to be cathode minus anode. And this is telling me the overall potential of the cell, right? The whole cell potential is based on how many electrons ended at the cathode minus how many are left at the anode. That's it. All right. I guess I'm gonna Alright, so let's say I have 2 half cells. I want to figure out what is the overall E0 for the cell. Right, so I know the E0 for the cathode. I know the E0 for the anode. How do I figure out what the overall E cell is? Yep, subtract. Okay. What would be the units of this? Volts, right? Big V, volts. Is this a spontaneous cell then? Yes. Right? So we would expect this one to go on its own. Okay. Questions about that so far? Again, good warm-up. Okay. The question is, where did I get those values to use in this? Right, these are all standard values, right? If they have that 0 up there, it means standard state, means I can look them up in the table. You have a table that looks like this, something like this in your book. If you don't, just print out this one specific page out of your PowerPoint. It has every half reaction with every voltage. So this is a handy table to have around, especially when you're doing maybe your homework and whatnot. So, I will either give you a table or I'll give it to you in the problem somehow. I haven't decided which one to go with. But yes. No, I'm not asking you to memorize this. That'd be insane. No need for that. Plus, it's a very good table. I like it. So looking at this, it's a little hard to tell. Let's see if I can pull it up here. Wait for it to focus. Oh. Alright, so it says standard electrode potential is at 25 degrees Celsius. What is the thing it says right underneath it, if you can read it? This entire table is only reduction half potential. So everything listed here, if you look at anywhere on the table, right, all the reactions have electrons as reactants. Can you have two reduction half reactions together? No, you can't. You can't have that. So how do we get around that? Alright, so on this table, any table you look at will only list reduction potentials by convention. Alright, so we find E cell by measuring the difference between these two things. And because I'm looking for the difference, even if I want to use, let's say I want to combine this iron plus 3 to make iron solid, and this chromium plus 3 to make chromium solid, I do not change the value or the sign of the value in the table. So I'm looking for the overall difference. So you just use it. You just use the value. Even if it's written in the wrong direction, do not change the sign. That's so important. I'm going to write it in big, huge capital letters. You should start, sign it, circle it, because you're going to do it, and you're going to be wrong. So do not. So to use the reverse reaction off of the table, otherwise known as the oxidation reaction, so don't do it. Don't change the sign. Use it off the table as written. Alright, so let's do a little practice problem that involves using the table. Alright, let's say for example I have almost around space there. I wrote too big to begin with. Alright, I have a chromium solid and a nitrate ion and 4 protons making chromium plus 3, nitric oxide, and water. Interesting question. Oh, question first. Yes, that's 2H2O. Was this reaction balanced in acid or in base? Acid. What's the dead giveaway that I balanced it in acid? I got protons and water. Right? That's just a side question. Doesn't really apply to the question at hand. But good, good. All right. Let's talk about who is being oxidized. Who's being oxidized? Chromium. How do you know the chromium is being oxidized? Yep, starts with a solid. You do not have to because it's already balanced, but I find it easier to do this as good practice, and we can find it on the table. Right, you can see it's already balanced because over here it's 4 pluses and 1 minus, and over here I got 3 pluses. And then mass balance, we're always good on that. Alright, so that's the oxidation half. So, by default, right, everything else must be referring to this. Alright, so everything's left over. And that's the reduction. What? Guess? Guess. Yep. Alright, so I want to find E0 step. Alright, so which one of these two reactions, the chromium or the nitric oxide reaction, which one is occurring at the cathode, number 1 or number 2? 2, right? That's reduction at the cathode. So let's go to the table. Let me figure out where it is first, that way I can show it to you easily. Alright, so I want the one that has chromium, reduction. I want to use the one that has the NO3 minus and some protons and some electrons. Right, I want the one that matches this half. So we find it right up here. Right? Which way's in focus? There we go. NO3 minus, 4 protons, 3 electrons make NO and 2 H2O. Imagine how handy that would be if you're using this table while doing your homework, because it has all the half reactions already balanced. Just saying, it's a time saver. Alright, so I have this value 0.96. Write that down. Alright, now I want to do the oxidation half reaction. So I need to find something that has chromium and chromium plus 3. I got 2 options here. Which way is in focus? Oh, that's a little bit. I got chromium plus 3 and 1 electron makes chromium plus 2. I got chromium plus 3 and 3 electrons makes chromium solid. Which one's the better option? This one, right? Because it's the one you want. It matches what you have. The value for that is negative 0.73. It's in the wrong direction. Should I change the sign? No. No. Put your hand up. No, don't do that. No, friend. Save yourself. Don't do that. When I combine these two things in this manner, where this is the oxidation, that's the reduction, is this a spontaneous reaction? Yes. What if I had flippy-floppies? What if I chose to have this backwards as the oxidation and that as the reduction? I would have negative 0.73 minus 0.96. Would that be a spontaneous? No, it wouldn't. So the order in which these things are occurring in tells you if it's spontaneous or not. So that's why you have to leave the sign as is, because you're subtracting subtraction. It's the only way it becomes a positive thing. Good? Alright, I will stop there on that bit of excitement. You guys, whew, this is the best part of chemistry, and you guys are just not into it yet. I got days and days and days to convert you.